Okay, so Andre, up to you.
Okay, thank you very much, Alvaro. So it's my pleasure to introduce Serge Cantat from Rennes, who kindly agreed to give a first talk of this Zoom seminar. So please, Serge, go ahead.
Thank you. Can you see my screen or not? I'm sure.
No.
Okay, I will. Because someone else is sharing.
I am. Wait. Now you can share.
Yes, I can do that. I want to share this one. Is it good now? Perfect. Is it okay now?
Yes, now it's perfect. We see it perfectly.
Okay, so let's start. And first, thank you for the invitation. It's very nice. I like the title of the seminar. You know, it's not clear for me whether it's groups of algebraic transformations or groups of transformation which are algebraic groups. I guess both of them, and we will see both of them. Okay, so my talk is based on a joint work with Christophe Dupont and Florestan Martin-Baillon. And the title I chose was the product replacement algorithm. It's something which has been used by people who wanted to produce random elements in finite groups. Okay, so you want to write an algorithm that produces, given a group, a finite group produces a random element in this group. But this is the beginning of the story, but I will quickly move to a more advanced project, which concerns, in fact, not finite groups, but compact groups. Okay. So this will be based on very classical results, like the Jordan theorem for finite subgroups of matrices. And there are beautiful papers on the subject by Emmanuel Breuillard, Tariq Gelander, Bill Goldman, Masatake Kuranishi, who's the same Kuranishi as the one from deformation theory, Alexander Lubotsky. So I won't cite many names in the rest of my lecture, but so most of the arguments are coming from these papers. Okay, so I will start with finite groups, and I will slowly move to compact groups. So let me explain the problem. Okay, so the group I will look at first is the free group on n generators. Okay, so it's not a finite group. It's just a group which is generated by n elements. There are no relations between the elements. So an element in my group in Fn is just a reduced word in the letters AI. Okay, so for instance, A1, A3 to the -7, A2 to the 2, A1 to the -1, A4. This word here is an example of an element in my free group. And the second player for today will be the automorphism group of the free group. So what is an automorphism of Fn? Is just an automorphism of this group as an abstract group. Okay, this means that you have to specify where you send the generators, A1, A2, up to AN, and you must map them to a new set of n generators of the free group. Okay, for instance, with two letters, two generators, you can map A1 to A1, A2 to A2, A1. If you do that, you get a new system of generators because you can recover A2 from A1 and A2, A1. And so you get an automorphism of the free group. Okay, so that's the first object that we will look at, the free group on n generators and its group of automorphisms. And then what I do, I give myself a group. It will soon be a compactly group, G. And I look at the space of all representations or all homomorphisms from the free group Fn to the group G. Okay, so just all homomorphisms. And there is an action of the group of automorphisms of Fn on this space of homomorphisms. just by a precomposition. If you have a homomorphism, a representation, and you have an automorphism of Fn, which can compose the homomorphism rho with the automorphism phi. Okay, so this gives you a dynamical system. The space is the space of homomorphisms, and the action is the action of the group of automorphisms of Fn. Okay, so the group acting is this one, and the space on which it acts, it's a space of homomorphisms. Okay. Okay, and what I want to do is try to say, study this dynamical system. Okay. So the basic remark is that if you specify a property which depends only on the image of the homomorphism, then this property will define a set in the space of homomorphisms, which is invariant under the dynamics, under the action of the group of automorphisms. Because when you compose a representation with an automorphism of the source of Fn, you do not change the image. Okay. So for instance, if you say I'm looking at homomorphisms such that the image is finite and contains exactly 17 elements, this space is invariant under the action of out of Fn. Okay, so that's a basic remark that I will use again and again. Okay, so let me phrase this problem with concrete equations or parameters. What is a homomorphism from the free group to G? It's just n tuple of elements of G, because to specify a homomorphism from Fn to G, you just have to say where you map the generators. Okay, so if you choose a homomorphism rho and you define Gi to be rho of Ai, then you get a point in G to the n. And this is a one-to-one map between the space of homomorphisms and G to the n. So as a set, this is just G to the n. And how can you describe the action of the automorphism group using this identification of hom Fng is equal to Gn? How do you do that? It's simple, and this is related to the theorem of Nielsen, which gives you generators for this group of automorphisms of Fn. So what I'm saying is that the following moves generate this action, and this is the theorem of Nielsen. So the first things you can do, you can permute the Gi. Okay? If you permute the Gi, this corresponds to the automorphism of Fn that permutes the generators Ai. Okay. So that's the first thing you can do. The second thing you can do, you can pick one of the generators of your group and you replace it by its inverse. You still get a system of generators for the same group, so it's an automorphism. So that's the second move. And the third and fourth moves are similar. You can choose two indices, I and j, which are distinct, and you multiply Gi by Gj on the right or on the left. Okay, so these are basic operations, and these basic operations, when you iterate them, you get the complete action, the full action of the automorphism group of Fn. So you can forget what I was describing on the first slide. You just say, my space is G to the n. The basic moves I have are these moves, this transformation of my space G to the n. And I want to understand the orbits that I can get, starting with some n tuple G1 up to Gn, and moving with these moves. Okay, so that's the dynamical system we are looking at. Okay, so here is a conjecture which is one of the starting points in this theory. It's due to Vigold, and it says the following. You fix a finite simple group, and you fix an integer n, which is at least 3. Okay. Then the group of automorphisms of Fn acts on G to the n, and it preserves the set of homomorphisms which are surjective homomorphisms, which are epimorphisms. Okay, epimorphism for me is a surjective homomorphism. Okay, so the set of morphisms which are onto is invariant. The question is, or the conjecture is that the action on this space is transitive. Okay, so given two sets of generators of your simple group with at least 3 elements, you can move from one set of generator to the second one using this series of moves, permutations, inverse, and basic multiplications. Okay. And so why is 3 some kind of threshold, and why does the conjecture start at n equal 3? It's because a simple group, a finite simple group is always generated by 2 elements. This is a consequence of the classification of simple groups. So you need at least 2 elements to get epimorphisms, and 2 is sufficient. And then you need a little bit more space to move from one set of generators to another one. This is why you cannot take n equal 2. In fact, n equal 2 is not sufficient. You need to take at least n equal 3. Okay, but this has not been proven yet. This is still a conjecture in full generality. This has been proven for groups like PSL2FP. Okay, so if you take, as a finite simple group, you take PSL2 with coefficients in a finite field with p elements, and this conjecture is correct. It's satisfied. Okay, so what I will do is look at analogs of this conjecture where G is not finite, but G is compactly group. Okay, so I will replace finite groups by compact groups, compact Lie groups. And I will show is that there are nice results for large values of n. So what is very difficult in Wiggle conjecture is to get up to n equal 3. Here, what I will do is different. So the group will be compact, so it's more general, compactly groups, but n will be large compared to the size of G. Okay, so I have to explain what is the size of a compactly group. And to do that, I will first prove a simple instance of Wiggle conjecture when I allow n to be large with respect to the cardinal, the number of elements in my finite group G. Okay, so I need some definitions. So here, G is a finite group, and I define the rank of G, D of G, to be the minimal number of elements necessary to generate G. Okay. So as I said, a simple group is generated by 2 elements. So for a simple group, D of G is 2 or 1 when it is a simple cyclic group. Second number is what I call the incompressibility constant of G. It is defined as follows. If you have a set S in G that generates G and the size of which is larger than the incompressibility constant, in fact, you can reduce the size of the set and still get a generating set of G. So in S, there are elements which are not useful at all for generating G. You can remove them. Okay. And the third number I will be interested in is the chain length of G. It's the largest number of terms in an increasing sequence of subgroups, a strictly increasing sequence. Okay, so let's play with the definitions. So first, see the chain length is less than the logarithm of the order of G in base 2. That's simple. It's because if you have a strictly increasing sequence, at each step, the index between a group and the next one is at least 2. So at each step, you multiply the number of elements by at least 2. Since you reach the group G in L steps, 2 to the L is less than the number of elements in G. So you get this log 2 estimate. The incompressibility constant is less than the chain length. This is also easy. You pick a set S that generates a G, let's say S1, S2, S3 up to Sk. Okay, and you look at the group Gi, which is generated by the first I element in your set. If this sequence is not strictly increasing, at some step you are adding a generator which is not useful at all because you do not increase the size of the group you generate. So you could remove it, which means you could compress the set you had started with. Okay, so this is also simple. And of course, the minimal number of generators is less than the incompressibility constant because if you start with a set that generates a G, you compress it up to reaching the incompressibility constant, and then you still have a set of generators. So D of G is less than the incompressibility constant. Okay, so let's try to prove some kind of warm-up theorem. What my goal is to explain how you play with these Nielsen moves. Okay, so you start with a finite group G, and you assume that N, which is the N that is in the definition of the free group on N generators. So you assume that N is at least the number of generators, so the rank plus the incompressibility constant. And then what I am saying is that for such a value of N, the action of out of Fn on the set of epimorphisms from Fn to G is transitive. Okay, so this is the statement of Wigel conjecture, but not for n equal 3, for n large enough. And here large enough is this inequality that depends on the group G. Okay. In this context, I don't need to assume G to be simple. It's just any group, any finite group. Okay, let us prove this theorem. So you fix a finite generating set, H1, H2, Hd of G, where D is the rank of the group. Okay, so by definition, there exists such a set. Okay, so now you pick a generating set of G, G1, G2 up to Gn, with n larger than or equal to D of G plus the incompressibility constant. Okay, so if I want to prove transitivity for the action on this set, I simply need to prove that I can move G1, G2 up to Gn to this one, H1, H2, Hd with 1, 1, 1, 1, 1, 1, 1 after Hd. Okay, so n tuple of element with the D first element equal to H1, H2, Hd. Then I prove transitivity because I prove that any system of generators of length n is in the same orbit as this element here. Okay, so I will prove that, and it is easy. Here is how it works. So first, n is at least the incompressibility constant plus 1. Let's say I'm working with a group which is not a trivial group, so D of G is at least 1. So this means that one of the generators is somehow not independent of the other one. I can remove it and I still generate the group. So up to permutation, which is a type of Nielsen move, I can suppose that it is Gn, the last one. So Gn is contained in the group generated by the first n-1 elements. So I can write its inverse as a composition of G1, G2, or here I should have written n-1, up to G index n-1. So these generators. Okay. And then I can read the word written by W, and I multiply Gn by what I have in W. So I get a multiplication like that, which is generated by the basic Nielsen moves. More precisely, I'm using these ones. Here I can multiply on the right by some element which is not Gi or its inverse. Okay, so I multiply that and I replace Gn by 1 when I do that. Okay, which means that using Nielsen moves, I can just forget about all the elements in my list of generators that are redundant, which are already generated by the previous ones. So I do it again and again until I reach the incompressibility constant. And then I move from G1 up to Gn to G1, G index incompressibility constant, and then I have 1 at the end. And the number of ones I have here, because n is at least d of G plus this constant, this number of ones is at least d. Okay. So now I come back to H1. H1 is in G, so is in the group generated by the GI. So H1 is a word in these elements. So I can use Nielsen move to put a H1 in place of the first one. And I do it again and again. I'm using the same strategy as here, but to replace a 1 by H1, and then replace the next one by H2, etc., up to HD. And this I can do, and I still have a non-negative number of ones here, because n is larger than that. But now I have H1, H2, HD, and they generate G, so I can use the same trick as here to kill all the GI and replace them by ones. And then I use permutations to reach this element. Okay. So every generating set of length n by simple Nielsen moves, so by the action of the automorphism group of Fn, has been mapped to this single element. And this proves transitivity of the action. Okay, so you see it's really, really basic. Okay, let me give a second version of the same easy theorem. You fix a finite group and suppose that n is larger than d tilde of G plus IC tilde of G. So what is d tilde and what is IC tilde? It's the same definition as before, except I do it for all finite subgroups of G and I take the maximum over G. Okay. Then the previous argument will work for all morphisms with values in G. I just replace G by the image of the homomorphism. Okay, and what I get is the following. For every homomorphism from Fn to G, the orbit of the homomorphism is exactly the set of epimorphisms from Fn to rho of Fn, the image of Fn. Okay, and this is the type of result I want to prove for any compact Lie group. Okay, so to state it, I need some vocabulary. So I will talk about epimorphisms now in the sense of topological epimorphisms. So I will write epimorphism, but what I have in mind is topological epimorphisms, which means a morphism from Fn to a compact group H, such that the image is dense in H. So the closure of the image is H. And I will denote by epi of Fn with value in H, the set of topological epimorphisms from Fn to H. Second notation I will use is H0 like that. It's classical notation. It's a connected component of the neutral element if H is a Lie group. And this will be the discrete part of H, or if you prefer, the group of connected components. Okay, so here is one of the theorems we have obtained recently with Dupont and Martin-Baillon. You consider, so you fix some m. So m is some dimension. You fix it, and you look at the unitary group in GLMC. So m by m complex unitary matrices. Okay, so this is the compact group you look at. And now what I say that these results that I stated in the warm-up theorem holds for this group G in a topological sense if n is large enough. And so instead of this strange constants here, here it's simple. You can write if n is at least some constant times m to the cube. Okay, so if n is large enough in terms of m, and it's a polynomial relation, then the conclusion is the following. So you start with any homomorphism ρ from Fn to the unitary group. You defined H ρ to be the closure of the image. So it's the smallest closed subgroup containing the image. It's also a Lie group. And the conclusion is the closure of the orbit of Fn, the closure of the orbit of ρ under the action of automorphisms of Fn is exactly the closure of the set of epimorphisms with value into this group H ρ. And moreover, this is the same as the set of homomorphisms such that at the level of the discrete part, you recover, I mean, it's an epimorphism at the level of the discrete part. So let us forget for a moment about this second inequality. What I say that this second inequality says that if the image of ρ of Fn, when you take the closure, if it is connected, then the closure of the set of epimorphisms is the same as just all possible homomorphisms with value into Hn, into H. Okay. So we are looking at a dynamical system on a space of homomorphisms, this space here. This space is just G to the n. It contains H to the n. So homomorphisms with value into this group H, which is the image of ρ. And what I'm saying is that the closure of the orbit is exactly that, at least if H is connected. If H is not connected, then there is a group of connected component, H sharp. And you have to just look at homomorphisms such that at the level of connected component, it is surjective. Okay, so it's a complete classification, in fact, of closures of orbits for these dynamical systems. Okay, so I stated this theorem with the unitary group. I will give a second version of it, which is in fact exactly the same, but phrased in a different way. So first, let me explain why it will be the same. If you have the unitary group, of course, it's a real Lie group, and it's a compact real Lie group. Conversely, if you start with a compact Lie group, then you can embed G in some unitary group. In fact, it's a Peter Weil theory. Any compact Lie group has a faithful finite dimensional representation, a continuous representation. So the image is a compact subgroup of some GLMC. The unitary group is the maximal compact subgroup of GLMC. So the image of G will be contained in the unitary group. Okay, so every compact Lie group is a subgroup of a unitary group. And moreover, it's easy to show that a compact subgroup of GLMC is also a real algebraic subgroup. So if you don't know how to prove this and you are lost in my talk, do it. It's quite easy. It's nice to know and it's easy. In fact, it's better than that. The theory of compact Lie groups or compact real algebraic group is the same theory. Homomorphisms, I mean, continuous homomorphisms are automatically algebraic automorphisms, things like that. Okay, so here is a second version of the theorem, but it's exactly the same theorem. You start with any compact Lie group. Then there is a constant n of G, which depends on G. You can take n of G to be m to the cube, where m is the dimension of the smallest faithful representation of G, with the same conclusion. Okay, so if n is at least n of G, then the closures of orbits of out of Fn in the space of representation are exactly the subset of epimorphisms when you take their closure. Okay, so which is the same as you look at all possible closed subgroups H of G, and for each such subgroup you look at homomorphism such that at the level of the connected components it is an epimorphism. Okay. Well, I wanted to state this theorem because I think it's nicer than, in some sense, than the previous one, but it's completely equivalent. Okay, and this one is somehow better because I make the meaning of n is large enough, explicit and quantitative with respect to the complexity of the unitary group. Okay, second thing I want to say that this theorem is just the easy part in a series of results. The next step, instead of looking at a description of orbits and their closures, is a description of invariant probability measures, and more precisely, ergodic ones. Okay, and if you have a closed subgroup H in G, then H comes with its Haar measure, and this Haar measure you can put it on. You put the tensor product of this measure on H to the n, which is a subspace in the space of representations, and so you get natural measures which are invariant under the action of the group of automorphisms. And in fact, what we prove is that all ergodic probability measures for the action of out of Fn are of that type. Okay, so in fact it's a better result, but more technical and using more ergodic theory than this theorem here. So what I want to do today is focus on this theorem. Okay, so the closures of orbits. Okay, so first I want to discuss one thing. The thing I want to discuss is here I explain that I want n to be at least m to the cube. In the conjecture of Wiegold, n had to be larger than 3, something which is uniform, that does not depend on a simple group. But here I'm asking more than what Wiegold is asking for. I'm asking for complete descriptions of orbits, and for this purpose, I really need n to be large enough in terms of m. And here is an example to explain this phenomenon. It's just finite abelian groups. So let me explain the example first and how it is related to the theorem after. So you look at one of the simplest finite abelian group. You take you fix a prime p. Okay, so p at least 3, and then you fix a dimension d, and you consider the group A, which is fp to the d. So it's a d-dimensional vector space over fp. Okay, and then you choose n for the free group, the rank of the free group, to be exactly d. Okay, so we are interested in generating sets, or more precisely, lists of d tuples of elements G1 up to Gd in A, so generating A as an additive group. Okay, so it's exactly the same as a basis of A as a vector space. So an element here in our space of epimorphisms is just a invertible D by D matrix with coefficient in Fp. Okay, so G is just the list G1, G2, Gd. It's D column vectors. It gives you an element in GLD. And now what is the action of the group of automorphisms of Fd? I explained the Nielsen moves, and these simple Nielsen moves, in fact, correspond to elementary matrices with plus or minus 1 on the diagonal, because you can take inverses. So in fact, the action of the automorphisms, the automorphism group of FD on this space here of epimorphisms is just the action on the left of the group of matrices with determinant plus or minus 1. And so this action cannot be transitive. Okay, so it's an instance where the Wiggold conjecture fails, but the group, of course, is not simple because there are less elements in SLD than in GLD. Okay, so in fact, the number of orbits is p minus 1 over 2. So that's why I assume p at least 3. Okay. So what happens is that you have at least p minus 1 over 2 distinct orbits when you look at epimorphisms with values in this abelian group, and you choose n equal d. Okay. Okay, so now let me reverse the point of view. What I was doing is I was fixing a dimension m and look at the unitary group of dimension m. So I was working in GLMC. Okay, but GLM contains z mod p to the d, so it contains this group A. As soon as, I mean, for m larger, less than d. Okay. So what I mean is that all these groups fp to the d embed it into GLM up to d equal m. Okay. So this means that this fact that the action of the group of automorphisms of FD is not transitive on epimorphisms for abelian groups if n is equal to d, you will recover this problem if you choose n too small in the previous theorem here. Okay. And so what you get is that for the previous theorem to hold, so I wrote n is at least m cubed. For sure, you need n at least m with this example. Okay. Okay, so that's the statement. So first, for n large enough, we have a complete description of the orbits. Second, n large enough is at least m cubed in our statement. But in any case, even if the m cube is not optimal, and we will see it's not optimal, n larger than m is necessary. Okay, so what are the last ingredient from finite groups that I want to describe? Are ingredients that come from Jordan theorem. Okay, results that date back like 150 years ago or something like that. So let me spend some time of the theorem of Jordan. So Jordan's theorem. You fix M, and you look at all possible finite subgroups of GLMC. Then the statement is that if you give yourself such a finite subgroup, then automatically there is a normal abelian subgroup A in G, such that the quotient has less than, or I mean, some constant uniform J of M. Okay, so all finite subgroups of GLMC are abelian up to some uniform index that depends only on M. Okay, and for instance, if you look at the symmetry group on M plus 1 letters, it acts on in dimension M plus 1 by permutations of the coordinates. But this action preserves the linear form, which is the sum of the coordinates. Okay, so it acts also on the kernel of this linear form, and this gives you a faithful representation of the permutation group on M plus 1 letters in dimension M. And of course, this group of permutations does not contain any normal abelian subgroup except the trivial one. So J of M, the optimal constant, must be at least factorial m plus 1. In fact, this is exactly what you can choose. You can choose J of M to be equal to m plus 1 factorial, at least if m is larger than 71. And this is a theorem of Collins. In fact, it's very recent. It has like 15 years. It has been proven 15 years ago. Okay, but this is, I mean, m plus 1, factorial m plus 1 seems to be big. But I want to remind you that in my baby theorem, my warm-up theorem, we were looking at quantities like the number of generators or the chain length, which were less than a logarithm in the order of the finite group. So, and the logarithm of factorial m plus 1 is roughly it's m. It's m times log 2 of m by Stirling formula. Okay, so the second thing I want to say that many people know Jordan theorem. The number of people who know what I like to call the true or the nice Jordan theorem. I mean the number of people who know this theorem is much less. And let me state it first, or read the corollary first, and then I will come back to the theorem of Borel-Serre. You take any, let's say, real algebraic subgroup of GLMC, then there is a normal abelian subgroup A in the group of connected components such that the quotient has less than J of M elements. So what I stated here, this corollary, is exactly the same as Jordan theorem, but I replaced finite group by algebraic subgroup. And the conclusion is not for the group, it's for the group of connected components. Of course, if the group is finite, this is exactly the same result. And why is it, why can you prove the corollary from Jordan theorem? It's because, in fact, there is, given an algebraic group, you can find a finite subgroup F in G that intersects every connected component of G. Okay, so then you just have to apply the statement of Jordan theorem to this group F, and you conclude the proof of the corollary. Okay, and this theorem that you can lift, I mean, given any algebraic group, you can find a finite subgroup that intersects every connected component, is due to Borel-Serre. The version that I am using is due to Borel-Serre. And it's also known in much larger generality. And there is a nice paper by Michel Brion about this theorem. Okay, so this gives us some kind of uniform estimate for the complexity of a group which is contained, a finite group which is contained in GLMC. You see, these groups, or groups of connected components of algebraic subgroups, they are abelian modulo something which is completely uniform. Okay. And moreover, you see an abelian subgroup of GLMC, a finite abelian subgroup, you can diagonalize it. And so the rank of this group is bounded by M. The number of generators you need is always at most M. So that's another uniform constraint that you have on finite subgroups. So there is a normal abelian subgroup A generated by at most M elements such that the index is at most J of M, where J of M roughly is factorial M plus 1. This holds for finite groups. This holds for real algebraic subgroups. And since compact Lie groups are real algebraic subgroups, this holds for the groups of connected components of any compact subgroup of GLMC. Okay, so that's the first type of uniformity statement that I will use. A second type of uniformity statement is also something that depends on the classification of finite simple groups. I mean, the theorem of Collins also depends on this classification. So these two theorems that depend on it. Every finite subgroup of GLMC is generated by 3m divided by 2 elements. So to generate a subgroup, a finite subgroup of GLMC, there is a uniform bound on the rank, on the number of generators you need. It's roughly 3m divided by 2. Okay. It's easy to get constants, this type of uniform bounds without the classification of finite simple groups if you do not want to be as optimal as these ones. Okay. I will use them because I think these are nice results, but there are cheapest ways to reach the m cube that I have in my theorem. That's it. Okay, so that's the end concerning finite groups. And I want to spend a few minutes on the proof of the theorem. Let me just come back to it. So we have the group of unitary matrices. We will fix homomorphisms from Fn to G. And what we want to do is look at its orbit under the action of Fn. That is, we want to look at what happens to rho when we compose with automorphisms. Or if you prefer, let me say it again, you define G1, G2 up to Gn to be the image by rho of the generators of Fn. And you apply these Nielsen moves that I described, and you want to look at what type of tuples of elements in G you can get. Okay, so I want to describe something which I call automatic redundancy. Here it is. Okay. So you have a compactly group in some GLMC. This is not really important. Just the most important thing is that you have a compact group. And now you give yourself a representation from Fn to G, and you say that it is redundant if you can decompose Fn in a free product of two subgroups, okay, such that A and B are non-trivial subgroups of Fn, and B can be forgotten without changing the image. So when you restrict rho to the subgroup A, you take the image and you take the closure, you get the same closure. Okay, so the image, in the sense topological closure of the image, is the same when you restrict to a proper subgroup of Fn, but moreover, a proper subgroup which is a direct factor in such a decomposition as a free product. Okay, so that's the definition. Let me explain what it means in terms of generators. So again, you start with G1, G2, Gn, a list of elements in G of length n, and you say it is redundant if you can apply these Nielsen moves. I mean, there is a sequence of Nielsen moves that starts with G1, G2 up to Gn and moves this sequence to G1 prime, Gn prime, such that what? If you look at the first k elements, the group generated when you take the closure, so the index top means I take the smallest closed subgroup generated by the Gi prime. Okay, the k first one, they generate exactly the same closure as the n elements, that is exactly the same as what you had at the beginning. Okay, so G1 prime, G2 prime up to Gk prime correspond to generators of my group A here, or more precisely to my group rho of A. Okay, this is exactly the same. I mean, the two definitions are exactly the same under the correspondence, which associates to rho the list of images of the generators of your free group. Okay, and so here is the theorem, and that's the key technical proof, the key technical statement to prove the previous theorem I stated. Okay, so what I'm saying is that if n is large enough, every homomorphism from Fn to the unitary group is automatically redundant. And moreover, large enough means n has to be at least, and this is optimal in the proof I will explain, n of m, where n of m is 2m times m plus log 2 of the Jordan constant plus 1. Okay, so I did not state the theorem correctly. I should have said, let us fix m. So we fix m. Then if n is large enough, every representation with value into the unitary group is automatically redundant. Okay, and so now I can explain this m cube. If you apply Stirling's formula, you get, so here log 2 of j of m is m log m. You multiply by m, so you get m2 log m, and this is less than m cube. Okay, so that's where the m cube is coming from. In fact, my m cube in my previous statement is more like m2 log of m. Okay, so let me prove this redundance theorem, this technical thing. Okay, so it's a proof by induction on dimension. So let me explain this. So first, of course, every compact subgroup of the unitary group has a dimension at most m squared. Okay, so now I will define a sequence of numbers of integers by recursion for every dimension d which is less than m squared, less than or equal to m squared. So in dimension 0, I just take m plus log 2j of m plus 1. Okay, so it's this number here, this thing here. Okay. Then in dimension, suppose it has been defined up to dimension d. In dimension d plus 1, I take this constant, I put it here. I add the max of what I have been doing previously, and then I add 1 for safety. Okay. Okay. Then it's really easy to show that this is an increasing sequence. In fact, it's equal to the so the largest one is the last one, and it's equal to m squared plus 1 times m plus log 2 j of m plus 1, and because of this 1 plus m squared. So what I get is n of m is m cubed log 2 of m. Okay, so it's not as this m squared log 2 of m. So in the proof I will describe, the constant is not as good as the one I was announcing here, because we have to be more clever to get this better constant. Okay, and so now I want to prove this automatic redundancy by recursion on D. So I will prove the following statement. So for any value of D between 0 and the dimension of the unitary group, so m squared, if n is larger than nd of m, and if G in the unitary group is a compact subgroup of dimension between 0 and D, then any homomorphism from Fn to G is redundant. Okay, so if I first to initialize the recursion, I need to prove it for D equals 0, and for D equals 0, it will be a statement about finite subgroup of UM. And then I will do it for D equal 1, etc. Okay, so let's do D equals 0. Again, it's about finite subgroups. You pick G1, G2, Gn, n elements generating a finite subgroup of the unit of G of the unitary group UM. Okay. I will fix a finite generating set H1, H2, Hd of G, and I can do this with D less than 3m over 2 by the theorem of Kovacs and Robinson. This will not be useful for the proof, but this will be useful for an additional remark that I will do. Okay. So what I start with this n-tuple of elements generating G, and I want to show that there is redundance. So I want to apply Nielsen moves to produce a subsystem which is strictly smaller and generates a subgroup, the same group. And for this, I use Jordan theorem. So I decompose G in an exact sequence where A is a billion, the rank is less than M, and the quotient Q is small, its order is less than J of M. So its incompressibility constant is less than the log of that. And I set I to be this incompressibility constant. Okay, and now let's play again with Nielsen moves. So my assumption is n is larger than this n0 of m, which is m plus log 2 plus 1. So it's larger than the incompressibility constant of the quotient plus the rank of the abelian part plus 1. So first I look at what happens in the quotient. So I look modulo A. And I do some moves, as I explained at the beginning of the talk. I can do some Nielsen moves to reduce the length n and still having generators of the quotients. So G prime 1, G prime I still generate Q modulo A. And the last one all belong to A. So this I can do. Now the rank of A is at least is at most M. So the rank of the subgroup generating by the remaining part here, B, which is a subgroup of A, is also less than M. And with what I explained using the identification of space of generators with matrices in the example a few minutes ago, it is easy to deal with this abelian part. So by some new Nielsen moves, I can move the G prime I plus 1 up to G prime n to a set of generators of A of length at most M here. And so since n is strictly larger than M plus log 2 plus 1, there is at least one which appears. Okay. So it's exactly the same idea. So my time is almost over, so I will skip this remark and just say a few words on the second step of the proof and then conclude. So assume now, so this proof, so I was a bit quick, but this proof explains what happens for finite subgroups. It works also for, instead of finite subgroup, but for groups of connected components. And now you try to prove, suppose you have proven the redundancy theorem up to dimension D, you want to prove it in dimension D plus 1. So again, you have a G1, G2, Gn generating topologically, so as a dense group G, where G has dimension D plus 1. So first you play with the discrete part and you apply some automorphisms or Nielsen move such that the K first terms now already generate the discrete part of G. And you can do this because this is just initialization of the recursion. Okay, and then the last one, you can assume that they are in the connected component of G. So the last terms in this sequence are in the connected component. Okay, so now recall what is the definition of n of m in dimension d+1. It's n0 of m. So I already used this for the first discrete part. And then the max of what you saw in dimension less than d. So look at what happens for the last terms. If they generate a group which has dimension less than d, or equal to d, then you win by recursion. Automatically, you see some redundance, some repetition in the thing. Otherwise, K generates something of dimension d. So, sorry, the last term that generates something of dimension d+1. And you forget about the very last term in your sequence here. So you just take G prime K+1 up to G prime n-1. If you already generate something of dimension d+1, then it has to be the connected component of G by connexity and dimension, which means that the last term can be forgotten without changing the image of the homomorphism. This is exactly what I call redundancy. And if not, because of the +1 here, you win again by recursion. So the proof is very simple. Okay. So I'm sorry I already took 2 or 3 more minutes. Maybe I just want to say that you saw in what I already explained, you saw almost all technical arguments using these the way you use this product replacement algorithm, or which is the same, the Nielsen moves. What I want to add is what comes next concerning the theory of Lie groups. And the very last thing we are using is a result of Kuranishi, which is the following, which is the fact that every compact subgroup, in fact, here the version I'm stating is the version of Kuranishi plus what I already said for finite subgroups. So every compact subgroup of the unitary group is topologically generated by less than 2 plus 3m over 2 elements. Okay, so the version for semi-simple groups is the following one. Every semi-simple compact Lie group is topologically generated by 2 elements. Okay, that is, for instance, if you take the group SOK, the orthogonal group, you can find 2 elements in SOK which generate a dense subgroup of SOK. Okay, so that's the last nice result that we are using to prove the theorem. Unfortunately, the complete proof of the theorem is technical, and but it builds on these basic ingredients that I described and the strategy that I explained for finite groups. So I will stop here, and if you have questions, I would be happy to answer.
Thank you very much, Serge. So, are there questions from the audience? Some questions, no questions?
I have a question. So this is something I prepared because look at this. I would like to share a question that I recently discovered. I mean, I discovered the existence of the question. It's the second one. Forget about the first one. Suppose you have a homomorphism from the free group to SLMC. Okay, such that when you compose your homomorphism with any automorphism of the free group, the image of the first generator is unipotent. Does this imply that the image of the full group Fn is solvable? Okay, so let me describe a little bit the thing. So you have the free group. It contains a lot of elements. some of them can be part of a generating set of length n. These are called primitive elements. So an element in Fn is primitive. Let's say H is primitive if you can find H2, H3 up to Hn, such that H, H2, H3, up to Hn generate Fn. So it's an element is primitive if it is part of a basis of Fn as a free group. Okay. Primitive elements are the same as elements you get when you apply automorphisms to the first generating element in your free group. So when I am asking that rho of phi of A1 is unipotent, what I am asking is I impose that the image of every primitive element is unipotent. Is it sufficient for concluding that the image of the free group is solvable? If you think about it, I mean, you can replace Fn by the image of Fn in SLMC. You can take the Zariski closure and play with it. If you start playing with that, there are very nice questions from, I mean, for people who are used to study groups of algebraic transformations and subgroups of SLMC in this question, even from an algebraic point of view. Okay.
Okay, so thank you. So is anyone came up now with a question maybe? Then maybe I'll maybe have a bit question not related to the main subject, but maybe to this Borel-Serre theorem you mentioned, Borel-Serre-Brion.
Yes.
So is there anything like, do you have an example, for example, if instead of GLN you take the group of branch transformations or the group of automorphisms of affine variety? Of course, it's not possible to have finite group there intersecting all the connected components, but may it be finitely generated, or do you know something like that?
Yeah, this I don't know. Well, in fact, I suspect no. Okay, so so here is a nice problem for the Cremona group already in two variables. So you take the Cremona group in two variables, so the group of birational transformations of P2. And now what I will do is the following. So you look at birational transformations of degree D for some fixed D. Okay, so if you fix the degree, you get an algebraic set, and you can list the connected components, or irreducible components, sorry. So you look at the set of irreducible components of BIRP2 in degree D, meaning defined by polynomial homogeneous polynomial formulas of degree D. Okay, so and then the question you can ask is, can I find a finitely generated subgroup that intersects every connected component like that for all degrees? And I suspect the answer is no. I have no proof. You can even ask this for finite groups. So for finite fields. So you fix a finite field, let's say FP. You look, I mean, does there exist say a finitely generated subgroup of the Cremona group with integer coefficients, which mod P intersects every irreducible component? I think that the answer is no, and this should not be too difficult. But I have no proof.
Actually, I just remember now that for the automorphic group of projective varieties, this is not true, right? Because there are at least algebraic varieties with non-finitely generated discrete part.
Yes, this is not true, but this, yes,
Oh, right.
I agree with that.
But for
Also, it's
the
easy to
Cremona
show
group-
that it is not true for the automorphism group of the plane.
for the automorphic group of the plane. But for the automorphic group of the plane, in the sense you explained for the Cremona group now.
Yes. For the automorphism group of the plane, you have you can use Jung van der Kolk theorem and play with it, and but then you have to discuss more precisely what are the good notions for what we should call connected components. What I was doing in my answer is I fix a notion of degree. So birational transformations given by formulas of degree D. And I was looking at, for each degree, the set of irreducible components of this algebraic set. If you do that for the automorphisms of the plane, then there is no finitely generated subgroup that visits all components. But this is very specific to the fact that it is an amalgamated product, and
Thank you. Okay, so questions? No? So let us thank Serge again for a very nice and well-explained talk.
thank you.
And